Okay, well, let's go ahead and start. We have some questions from the audience. I think first of all for ARM, question was whether the Cortex-A78AE has passed ISO 262 certification. That's a package you're providing, I believe.
Sure. So I'll take that. It's on the path to it. We it's obviously at EAC, and we will, as soon as it reaches the relevant milestones for ISO certification, we plan to have it certified both for systematic and diagnostic at the highest levels.
Okay, good. Let's see, we had a question about ASIL-D, about time predictability required for worst case execution. I believe this also applies to the cache locking feature in the A78AE. The question is that cache locking helps, but do you have any provisioning in the rest of the high performance architecture for time predictability?
So I presume the question relates to real time and how you can provide deterministic bounds for computation. From a failure perspective, definitely things like the cache avoidance features and so on do help. For a Cortex-A class system, the bounds of real time are obviously not going to be in the microsecond. That's what we have a Cortex-R class systems for, IPs for. But at a system level, when paired with things like mesh networks, which can provide segmented cache accesses specific to a particular domain being a collection of cores running a thread, so that there is no contention, or using things like cache partitioning features, which are present inside the multi-core cluster, you can provide an element of predictability to threads, both in the face of safety failures, which is where the cache avoidance comes in, but even in general to thread level variability in terms of memory access and so on. So there are ways to bound it. It will not be bounded to the level Cortex R82 or 52 provide today. That's what the R stands for, real time. But people do use our Cortex A class CPUs for some of these next higher order deterministic applications.
Avi, since we only got to see a glimpse of your processor architecture towards the end of your talk, and you've seen the other discussions on functional safety features, could you say how do you account for functional safety in your processor?
Yeah, definitely. So our view on that is that plain old redundancy is kind of last resort. And we have a whole hierarchy of a safety concept, which is layered in different levels and domains. As a processor, there are elements that address it at compile time even by designing and defining the critical or more hazardous passes within the compilation flow and in the mapping to the actual hardware to identify which passes carry higher fit, which is the failure in time measure. So it's quantifiable to a certain extent. And during compilation, we also attribute or give some attribution to that aspect so that areas or passes with higher fit get special attention. Basically, they are either remapped or carry some local redundancy. We also have a variety of mechanisms for local sort of BISTs or internal self-checkers. And we also eliminate the need for areas which are not utilized. And for those, we eliminate the overhead. So it's pretty dynamic and kind of plays in concert with our software tools. The last resort, of course, is the ability to allocate some levels of redundancy. And since the architecture, as we said, is very domain specific, it's built from very small components that are very granular. And we can therefore allocate areas that are redundant as a last resort. And by that address a variety of root causes or sources of that are potential of getting transient or random faults.
Okay, great, very good.
Hey, Mike,
so again, currency attendees, go ahead and enter the questions. Yeah, go ahead.
Yeah, Mike, maybe I could just follow up on Avi's comment there. I think it's a good point to make that simple lockstepping of a processor is not going to work when we look at the performance requirements for semi-autonomous or autonomous vehicles. You cannot simply lockstep a processor that's delivering 10 terops or 35 terops unless you're doing it at the system level and you can afford the cost, and that cost goes to the consumer. So you need to be looking at more intelligent safety mechanisms depending upon the use case, depending upon the processor type, to balance that performance and safety trade-offs.
So let me follow up on that, because I did have some questions with ARM showing the picture of the domain versus the zonal architecture. And so, you know, it's fine when we're down at the lower level talking about the processor, but at the system level, is there a trend towards one or the other in terms of the overall system functional safety, whether you distribute the processing or you have a central controller, or do you need a hierarchical approach? So who wants to speak first on that?
I'll go, since I spoke to that slide. That trend is coming for reasons that I outlined earlier, which is the fact that it lowers cost, creates more software-defined architectures that can change in response to market technology or customer trends. And yes, both are coming. I mean, today we see already at ARM, our customers, our partners, deploying the domain architecture. But functional consolidation is here already. And I'm sure my colleagues in the call would have seen that too. Zonal is the next logical step, actually moving to physical and driven more by, I guess, automobile-driven considerations like wiring reduction, the ability to connect sensors more locally because at the end of the day, it's a spatial processing environment. But in terms of what that does to safety, that's a very interesting question. At one level, it makes this safety question more difficult because you are homologously consolidating applications of different attributes, as I said. Safety is one of them, but there is other virtual versus non-virtualized address spaces, things like real-time. I mentioned the levels of real-time versus not so critically real-time, secure versus non-secure. All these threads now have to reside on and share resources on a single platform, which in my case is a CPU, could be a chip. It will be a chip eventually. The question is now, how do you keep them separated? And it's not a unsolvable or even unsolved problem. Virtual channels, things like separate address spaces, physical partitioning with MPUs, region protection. There's all kinds of stuff that people have done to keep logical machines separate while keeping them physically co-located. The catch is that we assume the integrity of the hardware in all these cases. That's what virtualization is. Safety brings in the problem of you can't trust the hardware anymore. Now, how do you ensure that the portions that are not affected by the failure are still able to protect themselves, ideally, from the failure, impact of the failure? That's fault containment, and equally continue operating when shared resource with what amount of shared resources are still around. And that's where the concept of mixed safety criticality comes in. And that's what that's the next big milestone on the journey that ARM is working towards.
Okay, anybody else have comments on that? How you look at the systematic approach to functional safety?
I would like to comment something for the benefit of the audience here. I think that there's an important notion that needs to be brought to the table, at least for the benefit of the audience, and that's the fact that it doesn't boil down only to functional safety on the component level, because there's a notion that's becoming more critical when you talk about perception system or smart systems, advanced systems, which carry statistical notion, and that is the safety of intent and functionality. And it's two distinct things. So first, you want to make sure that your components are behaving right, but you also want to make sure that from a system level standpoint, it behaves it was designed to behave. For example, and taking it back to my narrow domain of neural networks statistically makes a mistake, and that's its right intent and functionality. So you need to solve it at a higher hierarchy level at the overall solution, because inherently you would get some errors that are not because there was some bit flip or a random fault, but that's the way this machine behaves, and it needs to be taken into account. It's a whole new domain that's coming into this field, and more so with autonomous vehicles.
Yeah, I'm glad you brought that up. I actually, the same thought that, we're talking about the hardware, but, some of the more well-known failures, for example, with Tesla Autopilot were really due to software. Also, I think with the Uber test vehicle, same kind of thing. So how do you test for that? You said intended function. Well, if it was programmed to think a bridge, a truck was a bridge, how do you test for that? I mean, the software issues seem to be huge here.
Yeah, maybe I'll start, and then probably my colleagues can complement. But from there's no good answer yet, and people are working on better and better answers. Part of the answer is to ensure at the system level that you get freedom of interference, in the sense of different channels that can kind of collaborate to make a proper verdict or a better verdict. There's a lot of effort in simulating those outliers. And last but not least is the fact that you need to define what is the intended functionality. And that's a challenge. But for example, if you know where the system should fail and not just where it should succeed, then you know how to confine it or to detect even that its failure is right. This is a failure, and then you need to kind of complement it with something else that could cover that space, like other type of sensor.
Yeah, right. Other input on that?
Yeah, I would agree with that. You can only build a design up until what its purpose is. You verify the graphs upon which it has been trained. You certify your software against that use case, that use model. But then there are cases such as the different pedestrian crossing the road, where you're not going to be trained for that particular instance, in which case you need a safe execution model or engine next to that ADAS engine, or within the ADAS engine, that takes control in such circumstances to take the car to the side of the road, or take it to a known safe state before a critical issue can occur. So it most definitely needs to be looked at from a system level perspective. Us as IP providers, whether it's ARM, whether it's Synopsys or whoever, we're providing the building blocks, the components, the software, the hardware, the tools that allow our tier ones or our OEMs build the solutions for their particular use cases to deliver to the required application. And from a safety perspective, it's distribution of that safety depending upon the application in the ADAS. It's going to be a combination of mixed criticality for safety fusion type functions in the RISC processors, and then you're going to have safety embedded within the higher end DSP NN processors for localized safety detection.
Sure, right. It just seems like this calls for lots and lots of testing as well.
Like it's going to be anything.
Yeah, go ahead.
No, anything at the neural network level inherently is a statistical operation. There is going to be some failures even in the application level. So SOTIF is not a solved problem. We are grappling with that too. I mean, obviously there are statistical answers there that the ecosystem industry has to align on. But diversity of hardware is one angle to that problem, and definitely deploying a CPU or deploying some accelerator in a limited form to perform some of these macro operations are stuff that are approaches that could help in alleviate this problem. But key focus area, definitely something that we hope to have something. So,
well, along with the all of the hardware functional safety standards, we have the tables, ISO 262 and others. What's happening as far as standards for testing and software for the AI functions? Maybe a standard test set at least to cover common cases. We had the example of pedestrian crossing, for example. How is that being addressed?
So it's a bit diverse. Today it's not been fully addressed. There's what I mentioned, this SOTIF is not something that is out of thin air. It's basically there is an ISO committee for this specific case, but it's still kind of, it hasn't mellowed yet, I would say. And the other thing is that in practical life, Tier 1s and OEMs, they have their own set of tests and certifications that the ISO 26262 doesn't cover, and eventually ISO 26262 is basically a set of guidelines. It's kind of a way to properly to follow to get a properly designed system, but eventually the real life Tier 1s and OEMs are much more strict and have their own know-how and legacies, and they develop it in parallel. Not all of it I even know, but it's definitely out there, and a huge question mark on how it will proliferate down the road. It's easier on the ADAS side, and this is why I made the distinction on my presentation between ADAS and autonomous vehicle. It's distinctively different when you have man in the loop rather than rely on the machine, where the bar is much higher to guarantee the overall intended functionality, safety.
Right, right. Are any of you watching or participating in any of the efforts, like the Intel Mobileye is proposing an IEEE standard for the behavior of an autonomous vehicle, and NVIDIA has proposed something I think as well called force field. Are any of you working on those kinds of standards, participating in the development? Or you're not familiar with it?
I can't say I have. I heard of it, but I'm not close to it. I'm sure there are folks at ARM who might be.
I would say the same about Synopsys. Our team personally are not.
Yeah, it's just interesting that they're taking it to the IEEE to try to develop a standard there. But as someone wants, the good thing about standards is that everybody has one.
Yeah, it is, and maybe just a follow-on to the standards. I think it was Srikanth mentioned it earlier that 26262 is now with us for 10 years. It was a good start. It is a good reference from the fundamentals of safety, pretty much focused on the hardware, with section 6 on the software, and that is really on how you develop software that makes it bug-free. But to take us to the L2 plus, L3, we need to be looking at security. We need to be looking at user intent of the functionality. We need to be looking at safe execution and even availability of the processor. And that's been led predominantly now by some of the leaders in the industry, and guys like ourselves and ARM are working with those leaders.
Yeah. Well, let me ask you, I think, Fergus, you briefly alluded to it about malicious attacks. Functional safety is one thing, but what about tampering and spoofing in terms of the computer vision part of this system? I think there's been some stories recently about some people that spoofed the Tesla autopilot system by flashing images at the cameras. So how do you account for tampering and potentially spoofing if you're working on the AI part of the system?
From a processor perspective, you're looking at the type of security risk analysis of the security mechanisms that could infiltrate your processor. You're starting with a trusted execution environment. You're building your processor from the expectation that the software may not be legitimate, needs to be authenticated. You're assuming potentially that a fault could be injected either through the bus or directly through alpha type particles. A lot of the mechanisms and architectures that we use in safety can also be reused in security, from error detection within our logic, within our memories, to determine if a core is under attack. But certainly from a software perspective, you're looking at the authentication of the software before it moves into mission mode, various checks that can be carried out between the T-root HSM and the ADAS to confirm the ADAS processors running on the chip to confirm that the software is authenticated and running correctly. From the point of view of confirming that an image is correct as it enters your sensor, and that's a whole new area that I'm sure probably Tesla has some views on that.
Yeah, right. Anybody else on that? Tampering issues?
Absolutely. I mean, in a compromised system, there are so many levels at which, just like safety, you can attack security or you can plug those holes. I briefly alluded to some which solve or try to catch the issue at the lowest possible level, at the assembly level, if you will, in terms of trying to exploit some of the most common exploits that you see in the space in terms of buffer overflow and so on. There are, of course, higher level stuff where safety mechanisms actually do apply, as Fergus was saying. For example, if you're trying to run diversity at the algorithmic level, running it through the CNNs and then doing something slightly different using maybe GPUs or so, now it will just increase the burden on the attacker to be able to spoof it, because now he has to spoof both of them and spoof both algorithms in the same way, or at least attack both algorithms in the same way, which is a non-trivial task for even for a sophisticated attacker. And then there is, of course, the entire communication network, which is the pathway for attacks typically. Yes, checking images to make sure that they reached from one end to the other without being molested. That's a good one. CAN messages. Most automotive systems today, they have some sort of authentication of messages as they flow across the CAN network. Ethernet, again, separating high-value partitions or domains. And now I'm talking Ethernet domains from the more open ones using concepts like VLAN. We do that today in a non-automotive framework, changing that into an automotive framework and using the same methods of MAC lockdown authentication and so on and so forth. Or even if you want to do something at the application or network level, something akin to an IPsec, MACsec at the MAC level, are all in play for an automotive network. So connectivity, interfaces, and of course, actual code execution. There are methods being deployed in all these areas, and many of them, to Fergus's point, spot on. They definitely map onto safety and security. I mean, one is an act of God, the other is an act of man. So the solution can't be that different.
Good. Avi, do you have any comment? How do you take anti-tampering measures in your processor?
Yeah, it's I completely agree with my colleagues here that the things are tightly coupled, and eventually pair the attack vector. You need to address the you need to provide the right measure. In our case, again, there's similar notions to what was mentioned. There is the ability to ensure that what is intended to be loaded is indeed loaded, and that the root of or the origin of the software is trusted. In our case, it's a bit, it's only unique in the sense that the notion of software is slightly different because we are not running an ISA-based processor, so it's not an instruction-based. But it does allow the same concepts to be applied, but slightly different. But we do authenticate the source. And of course, the data itself, that's where machine learning actually come into play big time in terms of the algorithmic level, because you can authenticate a fake image versus a true image. It's hard to mimic a real image that's captured from a real sensor easily. And machine learning algorithms today can actually indicate that. So it's, again, obviously up to the tier one and the OEM whether they want to apply such an algorithmic concept, but the algorithms are there, and people can, like we said in the intended functionality from safety standpoint, you can also say it from security standpoint, and adversarial attacks, as they are called in this domain of neural networks, can be addressed to a certain extent, and tampering is not that obvious.
Okay, good. I wanted to, Avi, ask you again, you had, going back to the performance topic, you talked about non-neural versus neural operations and needing to take those into account. Were you referring to non-convolution layers or system-level host processor interactions or other things? What were the non-neural operations that you were talking about?
Yeah, maybe I ran through it pretty quickly, but generally speaking, any real-life system is not pure neural or non-neural. So it's not one way or the other. It's always a combination. The question is, what's the balance or what's the scale of each? For example, in many object detectors today, when you want to do a real object detection pipeline end-to-end, you run a heavy neural network to do the feature extraction and apply it to any frame that comes in. But on the and on the pre-processing and the post-processing of that network, there are elements that are algorithmic. There, you can call it signal processing elements, which are non-neural by nature. And these can be also heavy by their own. In the example that I gave on the slide, it was an object detector that had an algorithm called NMS, non-maximum suppression, which is also heavy by its own. And in that case, it may be an issue if you just analyze the neural part and give it enough juice to work very good. But if you don't give juice to the non-neural part or don't balance it with the non-neural part, you might end up with the non-neural part being the bottleneck, even it shouldn't be so. So that was the point there.
Got it. It is someone looking at the entire signal processing path. Yeah. Then in terms of, we all know, how unreliable TOPS are as a predictor of performance. Is there anything that a designer was looking to select a processor could look at? Do they have to just look at a reference for a particular neural network, or is there some potential correlation, at least, between the hardware and what they could expect from the final performance?
Yeah, it's a very good question and not simple answer. I'll split it into two. So of course, one thing is obviously that there is a linear effect. I mean, if you don't have enough TOPS, it's obvious that you will not be able to get out of the performance conundrum. But the bottom line from me is I'm a great believer of objective benchmarking. So I think that an objective benchmark would, if this overall algorithmic concept of neural network would prevail and remain like in the general purpose compute architecture, then there will be eventually an established set of benchmarks that people would compare based on those, like they do today with general purpose architectures, which as I shown in the first slide, like SpecInt or SpecFloat and the likes. And these would be, I think, the right prism for evaluating. The other part or the other option is if you have settled down to a specific architecture, a specific solution, you can evaluate your specific workload, and there's nothing better than actually measuring. But my bottom line is that there are a few that are well known and becoming more and more dominant, like MLPref, MBC, and AI benchmark for the mobile world. These are becoming more and more established as a suites for benchmarking a variety of networks, and a good prism, I believe.
Yeah, great. Well, I'm afraid we've run out of time. We're going to have a 10-minute break now. Thanks to all of our speakers. 10-minute break, and then we'll have a session on security, following on some of the topics we've been discussing. So thank you all.